Hey, fellow mathers. Before we get into this episode, we want to share with you how you can get access to free content, professional learning that will keep your students engaged and doing the math that matters. Get ready to go to this link, mathisfigureoutable.com/challenge.
That's right. Registration is open for the free Math is Figureoutable Challenge that's starting May 15th and runs to the 17th at 7 p.m. Central. We're going to have 3 nights jam packed with learning and routines that you can take straight to your classroom.
In these challenges, we have a great time. We do some math, talk about classroom experiences, give away super cool bonuses and prizes. You won't just walk away with routines that are naturally engaging and encourage your students to think mathematically. You'll also have a chance to win over 6K worth in prizes, including a few virtual PD sessions for your school. I'll be joined by my wonderful co host Kim and special guest Jenna Labe.
You can register at mathisfigureoutable.com/challenge for a fantastic learning experience. That's mathisfigureoutable.com/challenge. Now on to the show.
Hey, fellow mathematicians, welcome to the podcast where math is figureoutable. I'm Pam,
And I'm Kim.
and you found a place where math is not about memorizing and mimicking, waiting to be told or shown what to do, but it's about making sense of problems, noticing patterns, and reasoning using mathematical relationships. We can mentor mathematicians as we co-create meaning together. Not only are algorithms not particularly helpful in teaching mathematics, but rotely repeating steps actually keep students from being the mathematicians they can be.
So, in the last 3 episodes, we've been talking about one of our very favorite mathematical models, which is the ratio table.
Dun, dun, dun.
Yeah, in episode 129, we discussed using a ratio table to think about multiplication. And episode 130, it was all about division with ratio tables. And then last week, in episode 131, we had fun reasoning proportionally about solving proportions. In this episode, we're going to continue our series on the ratio table model by extending the work to equivalent ratios and fractions.
Dun, dun, dun. Now, if you teach younger subjects than that, you're still going to want to listen to today because it's going to impact how you and why you use ratio tables
Yeah.
with younger stuff like multiplication and division. And really, if you're teaching multiplication and division, you are teaching some fraction stuff. So this is going to be super helpful to kind of see that extension and how it relates to all the things. And it has been super fun to see the number of people on social media who are getting so excited about using ratio tables because A, it's super cool, and B, I think it's a relatively unknown model for many of us. And so it's been really, I mean, for me, it's been life-changing to use ratio tables. So check it out. A colleague of mine, dear friend, Karen Camp, who follows and does all the things, used 4 strategies this last week for Math Strat Chat. It was super cool. In one tweet, she got 4 strategies, and then she followed up with another tweet. And in the second tweet, it's like she couldn't fit all of them in one tweet. So 4 strategies to solve the Math Strat Chat problem in the first tweet, and then the second tweet she said, also a ratio table. Or actually, I put the in there. Also, ratio table, exclamation point. And then in parentheses, she said, listen to this week's podcast with a winky smiley face. Well, sweet. Hey, Karen, thanks for listening to the podcast. And I love that it encouraged you to use a ratio table to solve the problem. Right after that, another colleague, dear friend, Ray O'Brien, or @PieMathman on Twitter, he tweeted, was I supposed to use ratio tables? So to sort of answer to Karen's, I used ratio table, then he's like, was I supposed to use ratio tables? So you might be interested in how I responded to Ray and @PieMathman, thanks for your question. So I responded, I know people hate it when you answer a question with a question, but that's exactly what I did. I said, I would answer that question with a question. Could you use a ratio table if you wanted to? If the answer is yes, and you chose not to, okay, no problem. However, if the answer is no, in other words, no, you couldn't use a ratio table if you wanted to because you don't know what it is, you don't know how to use it, or you don't know what to do. If your answer is no, I'm adding a little more in here, by the way, than what was in the tweet. But if your answer is no, then I'd wish for you to own the coolness of ratio tables so that you would have the choice. Empowerment is about choice.
Yeah.
Okay, so that's the end of that tweet.
Mhm.
And Ray responded, I could use a ratio table. I do like them. Practically, when I see the question on my phone, I want to solve the problem mentally. So if I was on an iPad, I might be more likely to use a ratio table. I'm not going to get out a piece of paper and pencil, but that's me.
Sure.
So that's a huge, interesting answer, because what Ray is saying is, yeah, I own that representation. I could put my thinking, I could make it visible in a ratio table. I could use the relationships that I'm thinking about and I could put them in a ratio table. But then I'd have to get out a paper and pencil, and I don't want to do that. So I'm gonna record my thinking in a different way because I'm on Twitter and I'm responding to Mass Strat Chat in
Mhm.
that way. That is a completely way to go, Ray. Woo! Like
Yeah.
that. Then absolutely no, don't give me a ratio table, because it's the thinking, it's the strategy that we're interested in, not the model. The model is it is a model, and on Math Strat Chat, it's Math Strategy Chat. We're
Yeah.
interested to talk about the strategies. So then why bring up ratio tables? Because it's such a powerful model that we can use to make the strategies visible. And as we do that, that model can then become a tool with which we actually think. We use it as a tool, not just to record our thinking, but actually kind of as a tool in order to think. It can kind of nudge us to go, oh, well, if I've used that relationship, oh, and we can see other relationships can appear. It can be a helpful tool in solving problems. So
Yeah. Yeah.
ask,
So
go
go
ahead.
ahead.
So if you are asking yourself, should I be using a ratio table? The more important question is, do you own ratio tables?
Yeah.
And if you do, well, then it's your choice. You can use it or not. If you don't, man, join in, dive in, and help, and let us help you learn how to use ratio tables, so that then you have the choice. Then you're empowered to do what works best in that problem, whatever tool you're going to use best to help you with whatever strategy you're using. Then you're empowered to do that. Do you remember what you were going to say?
Yeah, I do actually. It's rare.
Yay! Yay!
You and
It's
I
rare.
look at the comments that people make for Mass Chat Chat, right? And we like to talk about them, and it's kind of one of our favorite things to do is share pictures of what people are doing.
Mhm.
But sometimes I wonder if people scroll through Math Strat
Mm.
Chat and see other people's thinking on ratio tables and just keep scrolling, thinking that they're all the same. That everything that's on a ratio table is one strategy, which is the ratio table strategy, which is not a strategy, right? In reality, they would have to look really carefully at what people are putting in the ratio table to understand their thinking about the problem.
Oh, that is so well said. It's almost like the comparison could be that you could look at an open array, a rectangular area model,
Hmm.
and you might, if the only thing you've ever seen on that area model is place value partial products, where somebody's always splitting the numbers into the tens and ones and tens and ones, and then they're multiplying all those parts. If that's the only thing you've ever seen on an area model rectangle, then you might be like, oh, they did an array,
Uh-huh.
without realizing they might have cut the pieces very strategically, and they might have used very clever partial products, and that's what's worth looking at. It's the
Sure.
way they cut the area up. Similarly, what you're saying is, in a ratio table, it depends on what relationships you use in the ratio table.
Hmm.
That's the strategy. So yeah, we would encourage you that as you look at Math Strat Chat or any ratio tables anywhere else, that you dive into what are the relationships that are being showcased, that
Hmm.
are being mentally, what's the word I want, the connections that are being made. That's what's cool, to look at in a ratio table, not just, oh, that person did a ratio table, click,
Right.
like, let me
Right.
look, let me go see if somebody did something different. No, like, it's like what they did in a ratio table is super important. Yeah,
Yeah.
yeah,
Yeah.
nicely said. And one of those places that's super cool that we can do with ratio tables is fraction equivalence.
Mm.
And you might be like, Pam, fraction equivalence, that's so easy. All you do is you write down, like, to find an equivalent fraction, there's this rule, there's this procedure that you can do. You just write down the fraction. Like I just wrote down, I don't know, why not 5/7, because it is. And say you wanted to make it equivalent to something with 20 firsts. And so I've got the fraction 5/7 equal, and then I have a fraction bar, and in the denominator I have 21 because I'm trying to create an equivalent fraction. And you might have memorized, I did as a student, 7 goes into 21 how many times, and then you take that number and you multiply it by the 5, and then you get the other numerator. And you might be like, yeah, Pam, that's what you do to find an equivalent fraction. Well, that might be a set of steps. That might be a procedure or an algorithm to find equivalent fractions. But what it's not is demonstrating understanding equivalent fractions. It's not
Mm-hmm.
using what you know about equivalence and building equivalence at the same time to find an equivalent fraction. I will never forget. Can you remember Garland Lincolnhoger?
Oh yeah. Yeah.
So, dear friend of ours who we have not seen lately. Come on, Garland, we got to figure out how to meet up with her at some point. Wonderful, wonderful lady who taught us a ton. We worked really early in when you and I were working together at the school you were
Yeah.
teaching.
Mm-hmm.
She said one day, so this is super early in my journey in learning that math is figure outable, and that that more than I ever knew was figure outable. So I'm diving into the research. I'm diving into my kids' classrooms. I'm working with Garland, and she said one day to me, I'll never forget. She looked me in the eye and she goes, "Pam, if you really understand fraction equivalence, you don't have to have any rules for fraction operations." And I said, "I'm sorry, what?" She said, like all the rules to do fraction operations, you don't have to know any of those if you actually understand fraction equivalence. That idea was so new to me. And so, like, fractions to me were all about which rule to do when. Don't look down on me, listeners. Not right now. Don't be like, "Pam, really? That's what you think?" Yes, that is what I thought because that's what I was taught. And if the rest of you are like, "Yeah, that's what we were taught." Yeah, that's what we were taught. So if that's your sort of focus of when you think of fractions and addition, subtraction, multiplication, division, and you're like, "Yeah, which rule?" And if I remember which rule to do and the steps in the rule, I'm going to invite you to consider if you actually understand fraction equivalence, we don't need rules to operate with fractions. So it's important that students actually have this feel and sense and understanding, not just this sort of vague conceptual understanding, so then we can learn the rule. No, 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 no. It's like actually really feeling fraction equivalence. In fact, do you
Mm-hmm.
remember, Kim, I came home from that day talking with Garland, and I said something to my personal kid. And those of you who've been listening to the podcast for a while know that I was hugely influenced by my oldest son. The way that he just kind of naturally mathematized was really the impetus. It was my inspiration for diving into all the math and all the things. And I went home to him and I said something like, "I can't believe she said that. Like, what?" And he, "Cameron, what do you know about fraction equivalence?" I was just super curious because remember, he's my inspiration. So I'm like, what do you mean? What? Tell me about fraction equivalence." And he looked at me, kind of cocked his head, closed one eye just slightly, and he goes, "Well, it's like if you cut the pieces in half, you would need to have twice as many to have the same amount of pizza."
Hmm.
And I
So
was
good.
like, "Say that again." Like he really had thought about the fact that if you'd cut the pizza into 7 pieces, so you had sevenths. If you had
Uh-huh.
sevenths of 1/7 of a pizza was one of those slices. If you cut them all in half,
Mm-hmm.
then you'd have twice as many pieces, right? But now you'd have 14ths.
Mm-hmm.
And so you'd have to take twice as many if I took one piece and I had 1/7, and now I've cut them all in half, I would have to take 2 of those 14ths in order to have the same amount of pizza as the 1/7.
Mm-hmm.
And you might like, "Well, that's trivial, Pam." No, no, so not trivial. Like that's a generalization that he was making that just was starting him in this idea that if you cut the pieces into even number of shares and you make a smaller fraction, then you got to have that's you got to scale up that many boy, I'm saying this to generals. So that's why he said it in halves, right? So it's easier to just say if you cut it in half, you have to have twice as many pieces in order to have the same amount of pizza. That idea, that sense of fraction equivalence is super important, and we can help that happen with fractions and ratios and with ratio tables. Ratio tables can be this model that can be one of the helps in making that happen.
Yeah. So we're talking about ratio tables today. And so let me give you a problem. And will you describe for us how you would use a ratio table to solve a problem?
do it. Let's do it.
Okay, so I'm going to give you 3/4 plus your 5/7 that you were just talking about. You were talking about sevenths. 3/4
Okay.
plus 5/7.
Okay, so to actually use a ratio table to solve this problem, I need to back up just a hair to
Okay.
say it's definitely not the first thing that I'm doing to build fraction understanding. So we're going to do all of the things and to build, like, what does it mean to have a fourth? What does it mean? So you said 3/4.
Sure.
What does it mean to have 1/4? And what does it mean to have 3 of those 1/4? What does it mean to have 1/7 and then 5 of those 1/7?
Mhm.
So there's lots of things that we're going to build with just fraction sense. And then we're also going to build a sense of addition and subtraction of fractions using a double open number line. So that
Mhm.
would be one of the models of choice first. So it would not be a ratio table first. It would, and I'm not going to go into that today. Maybe we'll spend a whole other podcast on that. But a ratio table wouldn't be the first model that I'd use. But after I have students using double open number lines, well, at least maybe I'll say it this way: after I'm helping students reason about the addition and subtraction of fractions, where I'm modeling their thinking using a double open number line, and we've got that going. And simultaneously, I've got students thinking and reasoning about multiplication on a ratio table.
Mhm.
Once we have those two main pieces, then it's going to be a very natural transition for students to use a ratio table to do the following for a problem like 3/4 plus 5/7. So I would say that students would look at 3/4 plus 5/7 and they would say, let's see, I need the same kinds of pieces. If I'm going to add fractions together, we need to have the same kinds of pieces to add them. Otherwise, I can picture 3/4 of something and I can picture 5/7 of something, and I can see that I've got more than one of a thing. That would be delightful for them to kind of, if they can picture those amounts. 3/4 is only 1/4 from one. 5/7 is only 2/7 from one. So I'm adding almost one to almost one. Gee, that's going to be more than one. So there should be this sense already of kind of the feel of what's happening. Then they can say, but in order to know exactly how much I've got to have the same kind of pieces. Let's see, fourths and sevenths. Now, I'm going very kind of general here. I would never start with fourths and sevenths to get students to get a feel for equivalent pieces. But now that we're there, we would have students go, let's see, what is fourths and sevenths? What do they have in common? Well, in this case, 4 and 7 are relatively prime. And so they could think, well, I know I could deal with 28ths because both of those I can cut fourths up into 28ths and I can cut sevenths up and make 28ths. Like if I have pizzas, I can cut them both up and make 28ths. Okay, cool. So I'm going to turn them into 28ths. Now, at this point, you might be like, well, yeah, then I'm going to do that procedure you said earlier. 4 goes into 28. No. Actually, what I'm going to do is I'm looking at a ratio table and I'm going to say to myself, 3/4. I've put on a horizontal ratio table. So I have 3 on the top and 4 on the bottom. And I've drawn a line next to it. And then I've drawn 28. And I'm saying to myself, what does it take for me to get from fourths to 28ths or from 4 to 28? Because I'm cutting those. It's like I'm thinking about fourths and I'm thinking if I can cut them all up into pieces to make 28ths. But how many pieces would I have, or how many times do I have to cut that fourth up to get 28? So I'd have to do it 7 times. It's kind of like Cameron said. If you cut why did we use 4 and 7, Kim? It's all right. It's just a crazy big number. It's just like Cameron said. If you're going to cut the pieces in half, then you get twice as many, or you would need to have twice as many. So if I'm going to cut each of those fourths into 7 pieces, then I would have 28ths. So on the ratio table, I've just said, to get from 4 to 28, that's times 7. So I've scaled from 4 to 28, and I've drawn a little arrow, and then I've written times 7. Then I would also have to scale the number of pieces that I would have. So the 3 also has to scale times 7. 3 times 7 is 21. So now 3/4 is equivalent to 21 28ths on that ratio table. Now, very importantly, I have to have a new ratio table to deal with the 5/7.
Right.
What? Pam, why can't we put those all in the same ratio table? I'm going to get at that in just a minute. I need a new ratio table to think about 5/7 to get to 28ths. So I've just written a tiny ratio table next to that one. I've got 5 on the top, 7 on the bottom. I've got 28 next to the 7. Drawn the line, 28 next to the 7. And I'm saying to myself, how do I get from 7 to 28? Oh, yeah, that's times 4. So then I'm going to have to scale up the 5 times 4 as well. And 5 times 4 is 20. And so the equivalent the equivalent to 5/7 is 20/28.
Mm-hmm.
I did those two things on ratio tables. I got the equivalence of 3/4 of 21/28. I got the equivalent of 5/7 of 20/28. And now I can say to myself, I literally can just reason, well, if I got 21/28 and 20/28, then I've got 21 plus 20/28 or
Mm-hmm.
41/28. So really, I'm using the ratio table to help me reason about what I need to scale, the numerator and the denominator, in order to get equivalent fractions that make sense in the either addition or subtraction of fraction problem.
What I love so much about what you just described is that if you've already, if you've already worked with kids a little bit with ratio tables, with multiplication, then
Mm-hmm.
scaling up is not a new idea. You're just bringing it to a new topic. And then when you said 21/28 and 20/28,
Mm-hmm.
there was space for me in my brain. I was like, oh, I'm going to do a little give and take here and create there wasn't this procedure of I'm going to add 20/28, 21/28, then I have 41/28, then I have to pull out the whole. When I had I was kind of writing as you were describing, and I had 20/28 plus 21/28, and I did a little give and take of 7/28. Does that make sense?
No, keep going. Why would
Oh,
you do that?
so I had written down 20/28 plus 21/28.
Oh, okay. Keep going. Keep going.
So then I said, okay, that's equivalent to, you're talking about equivalence, that's equivalent to 13/28 plus 28/28, which is 1. So I got 1 and 13/28. So no longer
Bam!
is it a little bit of like do another procedure on top of that.
That is so awesome. So once you knew that you were thinking about 20 plus 21/28, you
Mhm.
said, I'm obviously over 1, which you'd already discussed, right? Where we
Right.
knew we were
Yeah.
over 1. And you're like, so I'm going to pull that 1 out. I'm not going to add them together and get 41/28 and then have to think about what's the 1 in there.
Sure.
I'm
Yeah.
going to find that 1 right off the bat. So you're just like, well, I'm almost there. I'm just going to grab from the 1, grab from the 20, grab 7 to get to the 21. I know I'm re-saying it because it's so cool. So you made 20, you basically made 28/28, and then you thought, well, what's left over? Oh, the
Yeah.
13/28.
Yeah, and it just makes me think about, sometimes this is maybe off topic. Sorry, pull me back if so. But it makes me think about how, sometimes we hear from teachers, how do I give kids some experience using addition strategies or using multiplication strategies in the midst of my content if I'm a if
Mm-hmm,
I'm an
mm-hmm.
older grade teacher. And so these are just, right here we've talked about some addition strategies with give and take and some scaling for multiplication that
That are
is
happening
in the content.
inside
Yeah, it's inside
it.
the content that they're supposed to be doing.
Yeah, like fraction, addition, subtraction. It's just
Yeah.
super, super good. Yeah, I'm so glad you mentioned that. So teachers that are teaching fraction operations, as you're doing that, you could consider on the day you're about to do something like 3/4, or yeah, what was it, 3/4 plus 5/7?
Mhm.
You could consider doing a give and take addition string, and then
Mhm.
bringing out that idea as students are messing with problems like this, or scaling with multiplication, and then bringing out that idea as students are messing with fraction multiplication or fraction addition and subtraction.
Yeah.
Yeah, well said. Hey, so Kim, it also occurs to me that there are some things that we might just want to highlight, and I mentioned I was going to come back to it. Why did I use two different ratio tables to add three
Oh, yeah.
fourths and five
Yeah.
sevenths? Why
Yeah.
didn't I just? I mean, clearly, I could have just used a ratio table, wrote 3/4, three on top, 4 on the bottom, and then in the next entry, I could have put 5 on the
Mm.
top and 7 on the bottom. And then I could have added those together, right? So I could have had 3 plus 5 is 8. And then the 4 plus 7 is 11. And the answer could be 8/11. And
Mm.
clearly 8/11 is equivalent to, or not. Like it's not, right? It's an incorrect answer.
Yeah.
And you're like, Pam, no, you can't just add fractions. You have, like I said earlier, you have to have the same kind of pieces. You can't just add fourths and sevenths together. However, teachers of multiplication and division and proportional reasoning, haven't we been adding ratios in ratio tables? Consider a sticks of gum problem string. So if that's new to you, maybe we'll put in the show notes where you can go listen to a sticks of gum problem string. But basically, where we have a problem string, like if I have a pack that has 27 sticks in it, and so I just wrote down 1 to 27, and I've got 2 packs would then have 54 sticks. I did that kind of fast. So I have two entries right now. I have 1 to 27 and 2 to 54. And then if I said how many sticks would be in 3 packs, couldn't we add the 1 plus the 2 to get 3 and the 27 plus the 54?
Mm-hmm.
Now I'm sorry, I'm thinking of 14 things at the same time. So 27 and 54, is that 81? So wouldn't it be 3 packs would have 81 sticks? Well, that's actually correct. Wait, why can I add those two, that ratio 1 to 27, 2 to 54? Why can I add those together to get 3 to 81? But I can't add 3 to 4 plus 5 to 7 and get 8 to 11. And I recognize right now I'm raising kind of an interesting idea that if you've never thought about might be a little mind-blowing, maybe just a little bit. And I'm hating the fact I'm about to tell, but I'm going to tell. It has everything to do with the fact that in the sticks of gum scenario, those ratios are equivalent. That 1 to 27 is equivalent to 2 to 54. So I'm not talking about the fraction 1/27th plus the fraction 2/54ths and adding those together. I'm talking about equivalent ratios. 1 pack to 27 sticks is equivalent to 2 packs to 54 sticks. Since those ratios are equivalent, you can just add the numerators and the denominators in those ratios. I hate even using the names numerator and denominator. You can add the parts of those ratios together and get an equivalent ratio if the ratios are equivalent. Notice in our fraction addition problem that Kim gave me, 3/4 plus 5/7, those fractions are not equivalent. 3/4 is not equivalent to 5/7. So we cannot put them on the same ratio table because by definition, a ratio table is where all of the entries, all of the ratios are equivalent.
Yeah.
So that's kind of an important distinction to make that maybe now we can help you start thinking about, so that when you run into it, which you will, because you are teaching fractions. If you're teaching addition of fractions, ratios are appearing in your work. If you are teaching solving proportions with ratios, addition and subtraction of fractions is appearing in places. And so we as teachers need to parse out, when are we dealing with equivalent ratios and when are we dealing with fractions, part whole fractions that are not equivalent. And we need to help students parse out, so then what makes sense to do with those when we're dealing with those different entities, part whole fractions that aren't equivalent versus ratios that are. Go ahead.
I think you're bringing up such a really important point, and I think maybe for you and I, it's one of the reasons why context is so important when we're working with students on a ratio table, because they can really feel what's happening in the ratio table. And it's not just a series of digits or numbers that we're throwing at them. They really kind of own the packs and the sticks. And it makes sense to them that when you add packs of sticks together, packs of gum, then you're adding the corresponding sticks as well.
Yeah, and that makes so much sense that we can be grounded in that. So when students are adding fractions, then we can help them go, wait. Is this packs and sticks, or are we talking about 3/4 of a candy bar plus 5/7 of a candy bar? How much of a candy bar would we have? We're dealing with a part whole fraction, not with ratios, especially not with equivalent ratios. Yeah, nicely said.
Yeah. You also have some work in your workouts that you
totally
do some work with that. You want to talk about that for a minute?
Yeah, so we help you with this in my book, Lessons and Activities for Building Powerful Numeracy. Help parse out the different ways and kinds of different kinds of problems and different ways you can deal with fractions versus dealing with equivalent ratios. So if you're interested, totally check out Lessons and Activities for Building Powerful Numeracy, which has these super cool blackline masters called workouts. And remember that we need to have fraction understanding come before what we did today with ratio tables. And then once kids really have the sense and a feel for fractions, what they mean, then the ratio table is sort of this natural tool to use to create equivalent fractions.
Yep. We really hope this series, all about the ratio table, has been helpful so far. You will want to join us next week as Pam takes us to using the ratio table in higher math, and we wrap up with some pro tips you do not want to miss.
Dun,
Thanks
dun,
for
dun.
joining us each week. We are trying to grow, and we would love it if you'd support us by giving us a 5-star rating, or if you think we don't deserve that, reach out and let us know how we can improve.
Yeah, we would super appreciate that. And thank you for tuning in and teaching more and more real math. To find out more about the Math is Figureoutable movement, visit mathisfigureoutable.com. Let's keep spreading the word that math is figureoutable. Thank you for listening and making math more figureoutable.
To learn even more, make sure you register for our free challenge at mathisfigureoutable.com/challenge. You are not going to want to miss the evenings of May 15th through 17th, starting at 7 p.m. Central.
Math teaching, go register now. That's mathisfigureoutable.com/challenge. Join us to make math more and more figureoutable. And if you can't join live, register and we'll send you access to the recordings. We'll see you there.